You know, we're literally swimming in them every single day, but we barely give them a second thought. I'm talking about fluids, the water you drink, the air you breathe, the honey you put on your toast. They all have these secret powers. Today, we're going to pull back the curtain and look at the wild physics that let fluids do some truly incredible and sometimes unbelievable things. Okay, first up, something you've probably seen before. It looks like a little piece of everyday magic. You see an insect, maybe a water strider, and it's just standing on the surface of a pond. Casual as can be, like it's solid ground. So, what is going on there? How is that even possible?
And then there's this. You go to pour a glass of water, and whoosh, it just splashes right out. But then you grab the honey for your tea, and it oozes out in this slow, thick, syrupy ribbon. They're both liquids, right? So what's the deal with honey? Why does it fight so hard against flowing?
And for our last and most mind-bending puzzle, how can a bubble, it's just a puff of vapor, the most fragile thing you could imagine. How can that become so powerful that it can literally blast chunks out of solid metal, like a ship's propeller? It sounds completely made up, but it happens. And today we're going to find out how.
So let's start with that honey question. The answer comes down to one really important property that scientists call viscosity. And really, all that is a fluid's inner friction. It's how much it resists wanting to move.
The easiest way to picture this is to think of a fluid as being made of countless super thin layers, almost like a deck of cards. For that fluid to flow, all those layers have to slide over each other. Well, viscosity is just the friction between those layers. Honey has really high friction, so the layers stick together and resist moving. Water, on the other hand, has super low friction, so its layers slide past each other with almost no effort at all.
And the differences here aren't small, they're enormous. Take air. Water, at room temperature, is already about 55 times more viscous than the air you're breathing. But then look at something like engine oil. It's over 100 times more viscous than even the water. We're talking about massive differences in scale.
And this one property has some huge real-world consequences. That high viscosity of water is what creates the immense drag that a submarine's engines have to fight against constantly. But at the same time, the super high viscosity of engine oil is exactly what you want. It's what allows that thin film of oil to stick to all the moving parts in your engine, protecting them from grinding themselves into dust. So viscosity isn't just a number, it's a fundamental force engineers have to work with or against every single day.
All right, on to mystery number 2. We figured out the thick honey. So now let's get back to that water-walking insect. The secret here isn't about the friction inside the fluid. Nope, it's about a strange property that exists only on its surface. So how is this little guy staying dry? It looks like magic, but it's pure physics. It's not really floating in the water. It's standing on it. The reason is a phenomenon called surface tension. The very top layer of the water is acting like a thin, stretched-out elastic sheet, kind of like an invisible trampoline. So what's actually going on a molecular level? Well, if you're a water molecule deep inside the liquid, you're being pulled on equally from all sides by your neighbors. You're perfectly balanced. But if you're a molecule right at the surface, you've got all these molecules below you pulling you down and in, but almost nothing above you in the air. That strong inward pull is what tightens the surface, creating that skin. It's also why water droplets are spherical. The surface is always trying to pull itself into the tightest, smallest shape possible.
And this same power can actually make liquids defy gravity. Put a really narrow tube in water, and something amazing happens. First, the water molecules are actually more attracted to the glass than they are to each other, so they start to climb up the walls. Then, that surface tension, that elastic skin, grabs hold and pulls the rest of the water column up with it. The water keeps rising and rising until the upward pull from surface tension is perfectly canceled out by the downward pull of gravity on the water's own weight. And how powerful is this? Well, get this. The capillary effect is one of the key reasons water can get all the way to the top of the tallest trees on Earth. Those tiny tubes inside a tree's trunk use this exact principle to suck water and nutrients up from the roots, sometimes hundreds of feet into the air. That is the incredible power of surface tension.
And now for our final, and by far most dramatic, hidden power. We've seen how fluids can have internal friction and an external skin. But what happens when you move a fluid so fast that you literally tear it apart? This brings us to those destructive bubbles and a phenomenon called cavitation.
Now this just sounds wrong, doesn't it? We all learned that to boil water you need to add heat. But what if I told you that you could make room temperature water boil just by changing its pressure really, really fast? That is the wild idea at the heart of cavitation. It's not about heat, it's all about speed and pressure.
So here's how it goes down step by step. Imagine a propeller blade spinning like crazy in the water. It creates a zone of super low pressure right behind it. If that pressure drops low enough, the water spontaneously boils, right there, even if it's cold. And that creates tiny bubbles of water vapor. But then, the flow of the water immediately sweeps these new bubbles into an area of higher pressure. And that high pressure just instantly and violently crushes them, causing them to collapse out on themselves.
And the collapse of every single one of those tiny bubbles creates a miniature shockwave. It's like a tiny water jet slamming into a surface. Now, one bubble is nothing, but when you get millions of these bubbles forming and collapsing over and over again, it's like a microscopic sandblaster, just relentlessly hammering any surface nearby. The result is this intense pitting and erosion that can destroy even the toughest metals.
And that's exactly why cavitation is such a nightmare for engineers. It's not just that it physically destroys equipment, it also creates a ton of noise, causes heavy vibrations, and makes things like pumps and propellers way less efficient. So a huge amount of effort goes into designing special shapes that can slice through water at high speed without accidentally triggering this incredibly destructive hidden power.
So as we've seen, these aren't just some abstract ideas from a physics textbook. Viscosity, surface tension, cavitation, these are powerful forces that are always at play in the world around us, from what's happening in your kitchen to the deepest parts of the ocean.
So let's recap what we've uncovered. First, we have viscosity, that internal friction that makes honey so thick and gooey. Then there's surface tension, that amazing stretchy skin on a liquid surface that lets bugs take a walk on water. And finally, we saw cavitation, the raw, destructive power of bubbles that are born from low pressure, not high heat, and are powerful enough to tear apart solid metal. So the next time you see rain beating up on a window, or you stir a thick soup, or you hear the hum of a boat's engine, you'll know. You'll know the secret physics that's at work right in front of you. You know their secrets now. So the question is, what hidden powers of fluids will you see around you today?